Hello, everyone. We are the ASU Telemedicine Robot team. My name's Adwith.
My name is Miros.
My name is Part.
My name is Anna.
My name is Mateo.
We are the Capstone team for AWS. So before we get into the nitty-gritty details, we should probably tell you what the project's about and what the ASU Telemedicine Robot is. The ASU Telemedicine Robot was designed to make sure that we could transport medication and medical supplies to different rooms within an ICU. Essentially, the pain point we are trying to tackle is to help doctors, nurses, and any other medical personnel reduce their physical energy and mental energy when transporting supplies. We want to make sure that medical personnel can tend to the patients currently diagnosed with COVID-19 and not have to worry about moving from room to room. Also, thus reducing the risk of spread of bacteria. So now we're going to move into reinforcement learning, which essentially powers the whole robot. Reinforcement learning is a branch of machine learning. Essentially, we programmed our deep racer, which is the agent in this case, to interact with an environment, which is the hospital. The agent, which is a deep racer, executes an action based on a change in the environment. So we programmed our deep racer to execute an action, which is to avoid any incoming obstacles. For every obstacle it avoids, the reward function awards the deep racer a point. But for every obstacle the deep racer hits, the reward function penalizes a certain amount of points of the deep racer. This model is trained iteratively until a high enough accuracy is obtained and the deep racer is able to successfully avoid all obstacles. The agent essentially learns from its mistakes. In this image right here to the right, you can see a picture of the agent, which is the deep racer, on a track. And essentially, it's programmed to avoid the incoming obstacles within the environment. The action is steering when to avoid the obstacle, and it's again rewarded and penalized whether it's avoiding an obstacle or it hits an obstacle. So later on, you'll discover why we had to consider a different robot, but the NVIDIA JetBot was another robot we had to consider since the Deep Racer was not compatible with ROS or Robomaker. The JetBot is compatible with the ROS framework, and it can be programmed through Robomaker. It also does not need to be hacked to access the operating system, which means that we could just directly program it from Robomaker.
All right, now I want to talk a little about Robomaker and the ROS framework. Robomaker is a fully integrated development suite for a ROS application or robotic software. And ROS stands for robot operating system, which uses a lot of gives the robot a lot of functionalities and direction. For the purpose of simulating our robot, we're using a tool called Gazebo, which is already pre-installed on Robomaker, which makes the integration a lot easier. On the right here, we see a picture of the hospital floor that we're using for simulation purposes. The hospital floor was developed by an AWS Robomaker team, and we just had to figure out how to get that implemented onto our project. There's a link to the GitHub repository as well. Now a little bit about ROS. ROS is the operating system that controls the robot. And using Robomaker, we can take advantage of all of the benefits of ROS as far as like all the packages and all the libraries and dependencies that comes with ROS, which is really neat since Robomaker can take full advantage of that. In this picture, we can see our JetBot inside the simulation of the hospital floor. And later on, we can see some movements by the robot as well. So ROS consists of nodes and launch files. It utilizes the nodes for the functionality, and then it uses the launch files to invoke the nodes onto either the simulation or the robots. There's two different types of nodes and launches. Some are just to control aspects of the robot, and launch files are to invoke, which nodes to launch at what time, things like that.
Okay, so now I'll talk about our increment history and challenges that we face as a team. At the beginning of our project, we did individual and group research on robots and machines similar to our project. We also looked into learning the skills that we need to complete our project, like Python machine learning techniques. With this, we were able to set up our communication tools like Slack and Taiga, as well as begin to create our development environment on AWS. For the next sprint, we were able to complete the setup of our simulation environment, as well as begin AWS training badges that would help teach us how to use and get experience with AWS tools. While learning how to use AWS, we were also able to develop a reinforcement learning algorithm, which we'll be able to implement later on. At Sprint 2, we ran into some issues with AWS, so we mainly focused on creating 3D models of crates and trailers that would be attached to the robot in order to hold supplies and medicine. We were also able to meet with Amazon and have them show us how to implement a hospital simulation that we could use for testing. During Sprint 3, we were able to resolve our AWS permission issues, so we began working on implementing actual functionalities to robots in the simulation environment. We were able to finish our 3D models of the crates and trailers, as well as begin a dummy version of our server interface app that we will need for robot user communication. And then during this last sprint, we've been currently working on making actual progress with the AWS simulations that we cannot when we did not have access, and wrapping up the other tasks like our dummy app. Now I'll talk about the challenges of our team. So during the first couple of sprints, we encountered a few challenges. The main challenge that we faced at the beginning was a lack of communication, which led to misunderstandings in our team. We also have team members with opposite availability, so it was hard to meet. We found that people on our team had very different working styles, as some were more individual workers and others were more task-oriented that wanted more group discussions to allocate work. Thus, it became hard to assign tasks and complete work because there was not much communication happening. But during the beginning of Sprint 2, we were able to have an open conversation about how everyone was feeling and have been able to understand each other more and do work more efficiently. We also had some issues with hardware that we were given to use. The original robot that we were given did not have a working battery pack, so we had to delay development until our sponsor could provide a new one. Then during the last sprint, the sponsor wanted to switch the type of robot that we were using, so we had to begin development for a whole new robot. Now I'll pass on to Park to talk about the other challenge.
Another challenge we faced was having very limited access to AWS Educate, which led us to have simulation errors due to restrictions with permissions. And we had to find alternate development methods, such as using the cloud-based ROS Development Studio. Now let's talk about the material composite structure and design of our crates and trailers. So here we see the crate, two parts of the crate that we designed using Autodesk Fusion 360. And the material we've used is copper alloy that we'll talk about in the next slide. The lock mechanism we have on this lid is a simple lock mechanism that will allow for an external master lock to be attached. But this is just the first iteration. In the next iteration, we plan to use an electronic locking mechanism. And here we see two trailer designs that we plan to attach to the robot itself. And they've been designed in such a way that they can accommodate one crate on top of another, which allows for bigger or smaller loads to be transported throughout the ICU. And on the left, we have an alternate design of the crate that we wanted to make, so we could consider multiple designs and see which one fits best once they're printed. And we have found that copper alloy surfaces kill greater than 99% of gram-negative and gram-positive bacteria within 2 hours of exposure, which is a lot faster and quicker than plastic and cardboard materials. And hospital trials have also shown a reduction in bacterial counts, which tell us that copper surfaces are promising material to use for when hygiene is the sole purpose at a time like the COVID-19 pandemic.
Next, we'll be talking more about the mobile application and interference. So if you look at the top right, you can see a screenshot of what the app will look like. There's a camera view, so you can see what the robot sees, a navigation view, so an indoor GPS. It also displays what the current status is of the robot, what it's doing, what location it's at, what is the estimated time to the next destination, and then the number of medicine compartments that are available. And then below that, you can see the controls for the compartments. You can open, close, lock, and unlock, as well as an emergency stop switch. And it also includes every 2 hours, it will send you a notification to remind you it's time to clean the compartments. The reason why it's 2 hours is that's how long the virus will last on the copper material. And so next is more about the IDE and how it's made. It uses a Basic for Android, which is a variation of Microsoft's Visual Basic. It's a very the layout is very simple. It's not any beginner can use it. It's a very small size, so it doesn't take up a lot of storage. It's a startup company, but it's still slowly starting to grow. There's already some very well-known companies that use this, such as HP, Honda, NASA, Adobe, and Bosch.
Thank you for listening.